In our previous lecture, we studied the basic logic gates and saw how each gate processes binary input signals to produce a specific output. While these gates form the physical building blocks of digital circuits and PLC systems, it is Boolean algebra that provides us with a mathematical foundation to analyze, simplify, and design them. In this lecture, we will introduce the basic rules and properties of Boolean algebra. By the end of this lecture, you should be able to read, write, and simplify Boolean expressions and understand how they directly relate to the PLC control logic you will implement in the lab. On this slide, we see how Boolean algebra directly connects to the basic logic functions we studied earlier, and, or, and not. This table provides the link between three perspectives: the logic gate symbols, the verbal logic statements, and the Boolean equations. Let's walk through each row carefully. First, we have the AND gate. Notice the two inputs, A and B, entering the gate. The output Y is only true if both A and B are true. In Boolean algebra, this is expressed as Y equals A dot B. Here the dot symbol represents the AND operation, but often the dot is omitted and we just write AB. This is very important in PLC programming because series contacts and ladder logic directly correspond to the AND function. Next is the OR gate. Again, we have two inputs, A and B. The output Y is true if either A or B is true, or if both are true. In Boolean algebra, this is written as Y equals A plus B. Here the plus sign does not mean arithmetic addition, it means the logical OR operation. In PLC ladder logic, this corresponds to parallel contacts. If either path is complete, the output coil is energized. Finally, we have the NOT operation, also called inversion. This one only has a single input. The output Y is simply the opposite of A. If A is 0, Y is 1. If A is 1, Y is 0. In Boolean algebra, we write this as Y equals A, with a bar over the output variable. In PLCs, this corresponds to a normally closed contact. When the input is off, the rung is on, and vice versa. On this slide, we see some of the extended logic operators. Two of the most important ones are the NAND and NOR gates. Let's look at each one. The NAND gate is short for NOT AND. It works just like an AND gate, but then it inverts the output. So if the AND gate would normally output a 1 when both inputs A and B are 1, the NAND gate flips that result to a 0. In Boolean form, the NAND gate is written as Y equals A dot B with the bar extending over the combination. Next, we have the NOR gate, which stands for NOT OR. Like the NAND, it takes the basic OR function and inverts the result. Normally, an OR gate outputs 1 if either input A or B is 1. But in the NOR gate, the output is 1 only when both inputs are 0. In Boolean form, the NOR gate is written as Y equals A plus B with the bar extending over the combination. Up until now, we've looked at logic gates mostly by themselves. But in real-world control systems, logic circuits are almost always combinations of these gates. Boolean algebra provides a way to describe these combinations symbolically. Let's start with the first example at the top. Inputs A and B enter an OR gate. That produces the result A plus B. Then that output is fed into an AND gate together with a third input, C. So the final Boolean equation becomes Y equals the result of A or B with the result ANDed with C. Now, let's look at the second example. Inputs A and B go into a NAND gate. That gives us A and B bar. This means the output is 1 unless both A and B are 1. That result is then combined with input C through an OR gate. So the final Boolean equation is Y equals A and B bar, or C. This means Y will be on if either C is on, or the NAND condition is true. This slide introduces us to some of the fundamental laws of Boolean algebra. What's interesting is that many of these laws look very similar to the laws you already know from ordinary algebra. The difference is that instead of working with real numbers, we're working only with binary values 0 and 1. Let's go through each law. The first is the commutative law. For OR gate we have A plus B equals B plus A, and for the AND gate, A times B equals B times A. Next, we look at the associative law. This law tells us that when combining 3 or more variables, the way we group them does not affect the outcome. You may remember this same idea from arithmetic. It doesn't matter how numbers are grouped when adding or multiplying. In Boolean algebra, as long as the operation being performed is the same, the placement of parentheses does not change the result. Finally, we have the distributive law, which is unique in that it has two versions in Boolean algebra. The first equation looks just like regular algebra, where multiplication distributes over addition. However, the second expression is unique to Boolean algebra, and it can be very useful for simplifying expressions. Now that we have the basic rules of Boolean algebra, let's see how we can take a Boolean equation and directly convert it into a logic gate circuit. The expression we're working with is y equals a and b or c. The first part of the equation is ab, which represents an AND operation between inputs a and b. So the first gate we need is an AND gate with inputs a and b. The second part of the equation says plus c. In Boolean algebra, the plus sign means OR, not addition. That means we now take the output of the AND gate, combine it with input c, and feed both into an OR gate. The result of this OR gate is our final output, y. Looking at the circuit diagram, you can see exactly how this is built. Inputs a and b go into the AND gate. That output, along with input c, goes into the OR gate. The output of the OR gate is our final output, y. This slide shows us how to work in the reverse direction. Instead of starting with a Boolean expression and building the circuit, here we are given the circuit and asked to determine its Boolean equation. Let's carefully trace the logic step by step. We start with two inputs, a and b. Notice that each input also passes through a NOT gate. That means we are generating two inverted signals, a bar and b bar. Then, notice the input to AND gate. One has inputs of a bar and b, so the output is a bar b. Similarly, the input to AND gate 2 has inputs of a and b bar, so the output is a b bar. Finally, the output of AND gates 1 and 2 are fed into an OR gate. So the resulting output of the combination is y equals a bar b or a b bar. Today we've seen how Boolean algebra provides us with a powerful mathematical framework to describe, analyze, and simplify logic. The big takeaway is this. Boolean algebra is the universal language of logic. Whether we are working with physical relays, digital gates, or PLC programs, Boolean expressions provide the foundation for everything we do in control systems. In our next lecture, we're going to move from the mathematical foundation into real-world applications. We'll compare hardwired logic, the traditional method of wiring relays and switches together to control machines, with programmed logic, where the same control decisions are carried out by a PLC.